Cox, no, hands off. Complicated.
Ish.
Ish! Ha! Don't you ish me. Beyond human understanding, relative internal spatial coordinates are completely at odds with externally observed dimensions, so no.
Bigger on the inside than the outside doesn't seem too complicated to me.
I wanted to start with this short clip just to illustrate how one could tackle problems differently when faced with something unrealistic. One could ask questions and try to understand instead of being mind-boggled and discouraged from the unfamiliar phenomena. Without further ado, let me begin the presentation. In class, we learn about stochastic resonance of classical systems. Questions about an equivalent phenomena in quantum regime arises. In this presentation, I will consider a double well potential as a generalization for the classical case. Because quantum noise persists even at absolute temperature, the transport of quantum information should naturally be aided by quantum fluctuations. Stochastic resonance is a phenomenon in which the addition of noise to a weak signal results in an amplification and better detection of the original signal. Many modern applications, especially quantum computing, aims to reduce the noise related to those quantum qubits. It is exceedingly difficult to simultaneously isolate a quantum system from the noise and control it precisely. In fact, the act of controlling these qubits may be regarded as noise by itself. We would like to investigate and see if those intrinsic fluctuations can actually lead to stochastic resonance, this phenomena referred to as quantum stochastic resonance. Notice that quantum tunneling manifests itself and becomes very important at low temperature, when the system does not have enough energy to overcome a potential barrier by itself. Tunneling could still allow movement between the two-level system. The two-level system with the Mexican head potential is being connected to a ohmic heat bath. The Hamiltonian is given by the contribution of those three components, Hs, Hb, and Hi. We notice that we express them in the second quantization form. The random noise is given by psi of t, and it corresponds to a Gaussian statistic. This comes from the bath. This is known as the driven spin boson Hamiltonian. It describes the reduced quantum tunnel dynamic for our potential. We assume that the wells are periodic around the minima point, plus or minus x naught, and with energy biased epsilon. The bosonic operators b lambda dagger and b lambda corresponds to heat bath oscillations with frequency omega lambda, and the usual sigma correspond to the Pauli matrices. The time-dependent position operator characterizes the tunneling dynamic, and h bar delta is the tunneling coupling energy between the two lowest energy levels. We will now concern ourselves with a linear response theory. This is going to tell us how a quantum system responds to a perturbation or noise from the outside. According to linear response theory, the input signal and the average output response are related by the following integral. Notice that chi of t is the response function, and in fact we can obtain a closed analytical form for low temperatures and small bias. The linear susceptibility and the spectral power fluctuation could be obtained using the one-ended and two-ended Fourier transform, respectively. In the limit of weak driving force, we may separate the spectral power into two components. The first one stands for the spectral power for spontaneous fluctuations in the absence of driving, and the second one is the spectral power of the original signal. The spontaneous fluctuations are related to the linear susceptibility by the thermal fluctuation dissipation theorem. When investigating the periodic force, an expression for the spectral power density could be obtained by the same procedure advocated in the last slide. We notice that this expression has two roots that correspond to two delta functions. We define two measures. First, the spectral power amplification, denoted by eta, and the dimensionless spectral power amplification, denoted by tilde eta, similar to what Professor Wiesenfeld always does in class. The second measure, which might be more familiar to some of you, is the signal-to-noise ratio. defined by R or tilde SNR. We may introduce a scale temperature eta T and note that an increase in temperature causes a monotonic decrease of the spectral power. For a region of alpha smaller than 1, the spectral power amplification will not exhibit quantum stochastic resonance for the symmetric two-level system. On the left, plotted the signals-to-noise ratio of the semi-classical versus the dimensionless temperature. The solid line represents the dimensionless semi-classical signals-to-noise ratio with the tunneling corrections, while the dashed line gives the classical result without the quantum corrections. On the right, plotted the scale spectral amplification tilde eta for the symmetric double well as the scaled temperature for different frequencies of omega. Although the difference does not seem significant, it is definitely there. In conclusion, quantum stochastic resonance in deep cold reveals spectral power amplification. This occurs for the symmetric unbiased dissipative two-level system whenever the frictional strength alpha exceeds its critical value, 1. However, the signals-to-noise ratio measure occur only for those particular values of alpha greater than 1/2, smaller than 2. The effects of quantum tunneling depends both on the potential barrier shape and the dissipative mechanism of the system. The crossover temperature can be quite large, varying from 1 millikelvin to 100 Kelvin, depends on the physical system. Detailed investigation reveals that quantum stochastic resonance characteristically occurs when incoherent tunneling contributions dominate over coherent tunneling transitions. Moreover, in clear contrast to classical stochastic resonance and also to semi-classical stochastic resonance near and above T0, quantum stochastic resonance in deep cold occurs only in the presence of finite asymmetry between forward and backward escape path. Those, while classical and semi-classical stochastic resonance takes its maximum value for zero-biased, the quantum stochastic resonance phenomena vanishes in the deep quantum regime when the symmetry between the forward and backward dissipative tunneling transition is approached.